So it's my great pleasure to come, and today we are talking about our universe. And let's start from the sun. So we know that the sun is a star in our Milky Way, and there are hundreds of billions of stars in our Milky Way. And we know the Milky Way is a galaxy in our universe, and in our observable universe, there are at least hundreds of billions of galaxies. And our universe, by its definition, is the most complicated system in our universe because everything complicated is contained in our universe. But it's amazing that Einstein has said the most incomprehensible thing about our universe is that it is comprehensible, in the sense that we can understand our universe. This is amazing. So let us start by understanding how large is our universe. So it happens that I'm mentioning two numbers identically of the same order of magnitude, which is 100 billion. And literally everybody knows what's 100 billion, but if we are not Lee Carton or if we are not J.K. Ma, we probably don't have an intuitive understanding of what's 100 billion. So imagine a grain of sand. So there is a poem saying that to see the world from a grain of sand. So imagine a grain of sand, which is really small, and what's 100 billion grains of sand? That is about 400 tons, which means quite a few trucks. So if our sun is such a grain of sand, that means the whole Milky Way deserves a few trucks of sand. And it is similar for the story of our Milky Way and all the galaxies in our observable universe. If this is not yet intuitive enough, let us take a look at, so this is the Earth rising from the moon. And this is a photo taken in 1968 by the Apollo number 8 from the moon orbit. So our Earth and everything, everybody, and all the memories and all the human history is just in this blue star. But if we zoom a little bit more, so this is for the Voyage spaceship flying across the border of the solar system. And at that time, the engineers decided to turn the camera around to take a whole photo of our Milky Way, of our solar system. And this is part of our solar system, and the Earth is simply one small dot in this in our whole solar system. And if we zoom a little bit more, well, actually much more, and this is our Milky Way. For sure, now no spaceship is flying so far away to take a whole photo of our Milky Way. But we can reconstruct our Milky Way based on the observations, and our sun is somewhere here. So it is not even at the center of the Milky Way. And in fact, that is lucky, because if we were in the center, there are too many supernovae and things like that to make it worse. So we cannot really survive near the center. It's lucky that we are here. And again, if we zoom further, so these are according to all the galaxies we observe from the Space Survey program, like so-called SDSS, the Sloan Survey program. And the Milky Way is not even a point in here. So this is how our universe look like. So I'm talking about how our universe look like, but what is our universe after all? So actually, from the word universe, we can understand pretty much about how what is our universe. We can split the word into uni and words. What does that mean? So uni means one, and words means turn something into. So that means turn everything into one. And everything contained in the universe, make it into one, and that is our universe. And in Chinese characters, in fact, we have more precise meaning about the universe. So we call it 宇宙. So in Chinese character, if we split them, So the second character means all the time from the beginning to now. And the first character means all the space everywhere. So if you put space and time all together, that is space-time. And our universe is the space-time and everything contained in our space-time. So this is our universe. And this is the theme of our talk, that so what is the features of space-time, and what's the origin of our universe, and what's the fate of the universe. We know pretty much well about our current state, the feature of our universe. And for the origin and fate of the universe, we have theories which agrees with data quite well, but the research is still going on to make sure if that is the correct theory of our universe. And this is what we are going to talk about. So the first feature about the space-time is the age of the universe. It's amazingly interesting that we know the age of our universe is finite. Our universe was born, in some sense, 14 billion years ago. So again, 14 billion years is a really large number. But if we compress that 14 billion years into 24 hours, that means the whole human history is less than 1 second in that day. So it's really long history. And so this is the age. And what about the size of our universe? If my friends get to know that I am a cosmologist, typically the first question that they ask me is, how large is our universe? And I have a very scientific and responsible answer for that question, which is I don't know. And the next question they would ask is, okay, then is our universe of finite size or is infinite? And again, very scientific answer is I don't know. So why I almost know nothing? Yeah, there is a reason for that, which is our observable universe is of finite size. So why our observable universe is of finite size? This is because our universe has a finite time from its born to now. And so we know that light travels with a finite speed. So if we are limited by a finite time, that means if we think about the galaxies very far away from us, that the light has not reached us, even if the light starts to travel since our universe was born. So our observable universe has finite size. And that finite size is about 900 billion, it's about 90 billion, light years. So this is about the size of our observable universe. And the next question is, what are in our universe? So what are in our universe? The content of our universe is represented by this diagram. So here, first of all, our universe is very empty on average. By very empty, I mean here, so in the room, each cube meter, so there are 10 to the, I'm not sure, 10 to the 20 something items in every cube meter. But in our universe on average, so in per cube meter, there is of order 1 atom. It's really empty because between the stars, so the space is really vast and empty. And what are the matter content of such a empty universe? So we have 70% of something, we call it dark energy, and 25% we call it dark matter, and 5% of the matter are the matter that we actually know, which are made of atoms. And among the 5% which are made of atoms, there are 4% which are free hydrogen and helium, two lightest elements, and the stars and also the heavy elements take very small fraction. Let's say the heavy element is only 0.03% in our universe, which we are very familiar with heavy elements. They are in our body, but they are very rare in the universe, and some of them need to be made in very special situation, like be made by the supernovas explosion. And I mentioned something like dark matter. So what is dark matter? What is dark matter? So here, let me use this figure that imagine there is a galaxy. And so there are a lot of stars here and relatively very few stars over there. So if we look at a star here, we can approximate the galaxy as all the mass is in here. Then the astronomers can measure the speed of the star which is rotating around the center of the galaxy. So if we add all the masses up by adding all the observable stars, and we estimate how much gravitational pulling force is made by these stars, then what we would have inferred is that for the very distant stars, the rotation speed around the center of the galaxy should drop. This is because we are not having enough matter to pull the stars. But this is not what we have observed. And this is what we have observed. It's a completely different curve. And that means the gravitational force pulling the remote stars are much more compared to the mass that we have inferred by adding all the observational matter up, the observable matter up. So this is a problem. What are the missing masses? It looks really like a situation where we add up everything and we have still something missing. So there is a joke that in which situation 1 plus 1 is 3. Yeah, so people usually say that if you, in the situation that you made a mistake, then 1 plus 1 is 3. But as a physicist, there is another answer that 1 plus 1 plus a dark number that you are not seeing, it becomes 3. And in fact, in the history, there are a lot of such examples. For example, the discovery of neutrino, which is made by Pauli by the same reasoning that they observe apparently in some nuclear reactions, energy is not conserved. So the question is, are we going to abandon energy conservation at that time? And Pauli suggests that there are some particles emitted which we cannot see. And that particle eventually we saw. Now we measure it very well. So this is neutrino. And here is something similar, that there are some kind of matter that we are not seeing, and that's known as dark matter. By not seeing, we mean that the dark matter do not light up our universe, that does not emit light or absorb light. But still, we can see the gravitational effect of dark matter that is pulling other matter. So dark matter is really non-interacting in the sense that it's not emitting light, it's very lazy, but except gravitationally. So now we understand the gravitational interaction very well, but for the other interaction of dark matter, we know almost nothing. The only thing we know are the limits, that the interaction is really weak, and there are a lot of upcoming experiments going on to try to probe the nature of dark matter, how it interacts with the other kind of matter in whichever ways. So this is about the content of our space-time. And there is another important nature of space-time that I'd like to address, which is the expansion of the space-time. And this is actually the fundamental layer of modern cosmology. So to understand how our universe expands, let's take a math problem, expand a plus b squared. And I think you know the answer. But if your math is taught by a physical teacher, then probably you get a different answer. And this is how our universe works. That the objects that you see here, they are not really expanding with our universe, because these objects, like galaxies, they are a gravitationally bounded system. They are not expanding, but the space between the galaxies, galaxy clusters emerges and expands larger and larger. So this is what happens to our universe, and it is discovered almost 100 years ago. So discovered by Hubble, and probably earlier there are also a few other astronomers claim similar things. That if we measure the stars, the velocity of the distant stars, we are seeing that the distant stars, they looks to be running away from us. And using our current theory, general relativity, that means the expansion of our universe. So this is our current universe. And based on our current universe, the next questions that we are going to ask is, what about the past and what about the future of our universe? So if we are going to ask such a question, the first question we are going to ask is if the past or the future of our universe is different from the present one or is the same. So if our universe were in a steady state, then the past and the future of our universe would be the same as now, and there may be no point to ask this question. In fact, in the history, there are a lot of people thinking in this way, including poets and artists and also physicists. So, for example, this is one of the most famous poets in China, and what he is saying is something like the moon yesterday and the moon today are the same. So to extrapolate his meaning, so he tends to think, I guess, that our universe looks the same in the past and now. So this is very natural because our life is too short compared to the evolution history of the universe. So people tend to think so. And it's not only some poet. In Chinese, we mean it's not only Wen Kesheng who think about our universe like this. And also scientists, including Einstein, used to think about our universe in a similar way, that he first thought that our universe should be in a static state. But he is really annoyed by his belief. This is because when he solved his famous equation, the Einstein equation, which can tell how our universe evolved, he finds out that the solution is either expanding or collapsing. He cannot find a solution which is static. So to solve this problem, he by hand add a term which is known as the cosmological constant term. He add a term to make our universe static, and after a decade or so, the expansion of the universe was discovered by Hubble. And then Einstein regret a lot, because if he did not believe a priori that our universe was static, then he would have predicted the expansion of the universe. But he didn't. He by hand added a cosmological constant term. He missed that discovery. And it is actually a long story. And in 1998, not so far from now, that his added by hand cosmological constant is discovered. Yeah, but that's a different story related to dark energy. Yeah, so if he is alive until that time, he may not consider it to be the biggest mistake in his life. So now, nevertheless, now we know that our universe should evolve with time. And we'd like to ask the questions, what is the past of the universe and what is the future of the universe? They should differ from our current universe because of the expansion of the universe. So what is the past? So it's natural to imagine that because of the expansion of the universe, think about a volume. That volume was smaller when our universe was in an earlier time. But this is not the only effect in our early universe. And the more important effect is that there is a simple physical principle tells us if we compress a box of gas, the box of gas becomes hotter. If we do it the other way around, if we depress the box of gas becomes cooler. This happens in our universe due to the space expansion. So if we think time in this way, that it really look like we are depressing a box of gas, so the box of gas become cooler. So our universe originally was in a very hot state because it's smaller. It's like we compress the box of gas. It's like that the neighborhood gas is doing work to the box of gas. So our early universe was hotter, and the late universe was cooler. Our current universe is pretty low density and pretty cold, but the early universe is hot, and in fact, it is hotter than any experimental environment that we can achieve on the Earth in man-made experiments, including particle physics experiments. So what cosmology is doing is starting from the late universe and to do the observations and try to infer from the observations what happens in the early universe. So this is what cosmologists are doing according to the early universe. And here is the result of the research. So there are something that we know very little and something we know pretty sure. So this part we know pretty sure that of older so this is the time that our universe was born, and we know pretty sure around here that 400,000 years after our universe was born, the first ever light is emitted in our universe. In the sense that before the first ever light is emitted, our universe was so hot and dense, so light cannot travel. So this is the time, we call it recombination time. This time is where the first light emits. So here means earlier time, and here means later time. So at earlier time, our universe was so hot such that the atom cannot really exist, in the sense that the nuclei and the electron, so they cannot bind together because it is hot. So the light scatters with the electron so much that the light cannot freely travel in our universe here. And only after 400,000 years after the universe was born, the electron get binded in the atom, and the light from that time on can travel to us. And there are a lot of other interesting effects. For example, where protons and neutrons are formed, and the origin of mass, which is according to the so-called Higgs mechanism, and the Higgs particle is discovered 2012. And so there are some question marks. The question marks corresponds to something that we don't know. So here there are something we don't know, and here the so-called start of the hot Big Bang we know a little bit, and before that, again, something we don't know. So this is roughly the history, or we call it the thermal history of our universe. We call it thermal history because this side is very hot and this side become cooler and cooler. And so I already mentioned pretty much about the first light. Yeah, so the first light travel to us. So by first light, I mean the time that the photon, the light particle, can freely propagate. And once it can propagate freely, so can travel all through the 14 billion years to us. And because of the expansion of the universe, the first ever light gets redshifted in the sense that the wavelength of the photon, the wavelength of the light, become longer and longer. And now the first light is redshifted into the microwave band. And this is known as the cosmic microwave background. And the cosmic microwave background is discovered in the 1960s. And now we have many generations of the microwave background detectors. So this is the first generation, basically seeing a homogeneous and isotropic background. But starting from the 1990s, people are starting to see some structures on the cosmic microwave background. So that structure means that if we see from one direction and we see from the other direction, the temperature of the microwave background is almost identical, except that there are of order 10 to the minus 5 very teeny small fluctuations. And this teeny small fluctuations is measured more and more precisely. And the first time the fluctuation is measured is by Professor George Smoot, and I am proud to say that he's a professor at now at Hong Kong University of Science and Technology. This is the so-called cosmic microwave background, and we see the fluctuations there. And the fluctuation tells us two very important things, at least two very important things. The one thing is, if we look at the fluctuation, what are these fluctuations afterwards? So this is the time 400,000 years after the universe was born. And what happens to the fluctuation afterwards? So it is related to a question that where the structure in our universe come from. So we know that our current universe is pretty much inhomogeneous. There are galaxy clusters, there are galaxies. So where this galaxy come from? Actually, the galaxies in our universe come from the very small fluctuations at this time. So the fluctuation become larger and larger because gravity is unstable. So if somewhere has larger fluctuation, larger energy density, then it attracts the matter around it. So that part become larger and larger energy density and eventually become galaxies and galaxy clusters. And the rest of the space become more and more empty. So this is where the galaxies, the structures in our universe come from. So this is one question we can ask about the cosmic microwave background, which is moving forward in time. And the other question we can ask is, what about moving backward in time? So from the 400,000 years after the universe was born, moving backwards to ask at earlier times where this fluctuation come from. And where this fluctuation come from? And there is an amazing thing about these fluctuations. So we can actually tell by our eyes that the fluctuation on the microwave background, so this is a patch of the microwave background sky, and this is white noise. By white noise, I mean point by point, there are uncorrelated noise. We can see that this figure is very different from this figure. Yeah, first of all, the color is different. This is because I didn't find the same color. Yeah, but apart from that, you see that there are some clusters in this figure that, so let's say if here the temperature is very low, around the low temperature, the temperature tends to be low as well. This is different from the white noise, that if here the temperature is low, around there, so the temperature is random. To translate what I'm saying in other words, there are correlations between one point and the other point, microwave background, which is unlike the situation here, that there is no correlation in this white noise. So there are correlations, and technically we can plot the correlation function, the 2-point function, in the sense that I select one point here and select the other point with a fixed distance and see if there are some correlations between these 2 points. And indeed, there are correlations. And this is amazing and mysterious in the sense that if we imagine the photon travel to us from one side of the universe through the 14 billion years, and the photon travel to us the other side of the universe through the 14 billion years, and that photon has correlation between each other. This cannot be explained in the so-called standard model of cosmology, assuming that our universe from the start is made of some matter that we are familiar with, namely radiation and matter. By radiation and matter, I mean the particles which are relativistic or non-relativistic. In other words, if our universe originates from the particles, at the beginning of the universe, one side of the universe and the other side of the universe, I mean the observable universe, do not have enough time to talk to each other. So they are unable to have physical correlations. but from observation, we see the correlations. So we need to ask why there would be the correlations, and that points us to a non-trivial start of our universe. So here I have to say that scientists have no idea about what is the absolute start of the universe, but we can look back and back in time. And so here there is a artistic picture about the non-trivial start of the universe, which is followed by so-called cosmic inflation. Inflation is a stage in the very primordial universe where the universe expands exponentially. By exponentially, it means, so probably you know the story about the emperor has a chessboard and put one grain of rice in the first part and 2 and 4, etc. And then, so the whole country cannot afford the last spot in this chessboard. That is exponential expansion. And here it is the same situation that, so if our universe was expanded exponentially, that means in about 60 characteristic time scale, our whole observable universe can be made by smaller than our building block. By smaller than our, I mean the building block that we cannot probe this kind of distance in current experiments. And the cosmic inflation solves the problem about the long-range correlation in our universe. And technically, it's known as the horizon problem. So this is why inflation was considered to be the preferred theory, and in fact is considered to be the most successful theory of the primordial universe. But yet there are still some challenges. There are some questions to ask about if inflation is indeed the theory of our primordial universe. And if we answer the question very seriously, we have to say that currently we are not very sure about the question. Yeah, in fact, it's an interesting matter of state that if you ask some of the scientists, they are very sure, but not everybody is very sure. So this is the situation about inflation. For example, in last year on Scientific American, there is an article written by very established physicist Paul Steinhardt, who is very close to the level of Nobel Prize for 2 different areas, a very established scientist. And he is saying that cosmic inflation has serious problem. And in fact, he has an alternative theory to inflation, which is assuming our universe was contracting in the past and following a bounce to expansion. Yeah, we know for sure our universe currently is expanding, but so here the question is, in the past, was our universe in a faster stage of expansion, or is contracting, follow a bounce, and expand again? So here, yeah, don't get me wrong that this is not the most popular theory. Yeah, by saying that, I'm only saying that there are different theories of the origin of the universe. Inflation is the most popular one, but it's not the unique one. And interestingly, after this Scientific American article, there comes a group of 33 physicists who sign a letter saying that this article doesn't make sense. Yeah, but we know that science is not made by vote. It's made by observations. So the question, is inflation the true origin of our universe? So this question, still, we are not sure. And in fact, at HKUST, we did a lot of work on trying to understand if inflation is the origin of our universe or not. And what we are doing is making use of the nature of quantum particles in the early universe. And the quantum particles, amazingly, can be considered as clocks in our universe, in the sense that I'm just mentioning a few words about quantum mechanics. Yeah, if you don't know it, it doesn't matter. I will mention more interesting things later. Yeah, so in quantum mechanics, if you look at a particle and wait some time, then you will see that the particle changed by a phase. By change by a phase, what I mean is you can see the interference pattern between the original state and the later state of the particle. This is why we can see the experiments such as the double slit experiment. And by this idea, in fact, the change of phase can be considered as a clock. And by using that clock, we can measure the expansion rate of our universe in principle. By in principle, I mean I'm a theorist and I'm proposing the experiment, but the experiment yet needs to be done. And it's very challenging. But nevertheless, so it's a method to see if inflation is the true origin of our universe. Okay, so I'm probably become too technical at this point about quantum mechanics, but nevertheless, so let's come back. So this is the story about the origin of our universe. And now, what about the fate of our universe? So if we look at the future, what happens? What happens for the future? So before talking about the future of our universe, let's talk about the future of our galaxies. So here is a computer simulation about the galaxies. So there is one galaxy, and you see another galaxy coming. So ignore this one. So these two galaxies. And these two galaxies are coming closer and closer and closer to each other. So it's a very beautiful computer simulation. So let me allow it to run for some time. So you see these two galaxies are coming closer and eventually they merge. So they are flying around for some time and they are merging. Eventually, these two galaxies become a spherical galaxy. It will take some time for the merge event to happen and eventually become more chaotic spherical galaxy. And here, I have to say two things about this video. The first thing is it is a real computer simulation. It's not that we just using some software to make it up. It's a real computer simulation. And the second thing is one of these two galaxies is the galaxy which is closest to our Milky Way. And you might have guessed that the other galaxy is our Milky Way. So if we see the night Milky Way, beautiful sight about the Milky Way, we should appreciate that we live now. So if we live in 2 billion years later, then what we are seeing is not like this, but the small dot here become much bigger. If 3.75 billion later, this is almost comparable size to the Milky Way, and slightly later, so become pretty chaotic. And for sure, if we wait too late, so our sun got exhausted and well, we probably cannot live on the Earth. But assuming we are still doing observation on the Earth, this will be what's happening for the night sky, which is completely different from what we see now. But according to our universe, this is really not a big matter. So in our universe, the real big matter is our universe is dominated by dark energy. Yeah, so I particularly use this figure because, so if you recall, so he was not the first runner when he got started. And this is what happens for dark energy. But eventually, he surpasses all the other runners and become dominant. This is what happens for dark energy. And what's dark energy? So to see what's dark energy, let us recall a little bit about Newton's mechanics. So Newton understood one amazing thing, which is gravity is always attractive. And that explains a great number of things, including the trajectory of baseball and also spaceship. So if we throw something up, so even what the object I throw up is going up, actually is decelerating. Yeah, so gravity is pulling it down. So this means gravity is attractive. So the question, there is a similar question about our universe. If we imagine our universe as a collection of stars, and the collection of stars and galaxies, they are running away from each other. If I imagine, think about one star or one galaxy, that galaxy looks like I throw something upwards and the other galaxies are pulling it back. So our universe would have decelerated if we understand our universe this way. Similar to if I throw something up, it's decelerating upwards instead of accelerating. However, this relies on the assumption that gravity is always attractive. And we should ask about it. Is gravity always attractive? So if the answer is yes, you probably have learned a fake science or physics. And in fact, this is not what we have seen since 1998. In 1998, the cosmological observation see that our universe is not decelerating. Instead, it's accelerating. So the universe expansion becomes faster and faster. This means, according to our previous idea about gravity, it means there is some component which gives us some sort of anti-gravity, which is repulsive instead of attractive. The acceleration of our universe is amazingly small, according to our usual unit. If we count meter per second squared, it's 10 to the minus 10. That means if a worm move 1 centimeter per second, after 3 years, that worm move 2 centimeters per second. But considering the lifetime of our universe is amazingly long, longer than we can really imagine. So eventually, this acceleration of our universe becomes the dominant force for the future of our universe. And people are trying to understand what is the origin of this very particular form of matter. I have to say that currently there is no solution to this so-called dark energy problem. We don't know what is the nature of dark energy. And the best guess, the best theory is saying that the so-called dark energy is the vacuum energy, in the sense that in quantum mechanics, vacuum can have fluctuations, and this fluctuation can have energy. So this energy of the fluctuation has a very particular feature, in the sense that if we imagine we have a box of gas, and if we expand the box, the energy density inside the box of gas becomes smaller. But this does not happen for the vacuum energy, because if we have a box of vacuum, we expand the box, we have again a box of vacuum, a bigger box of the same vacuum, and the energy density does not change. So vacuum has very different feature from the ordinary matter, and in fact, it provides us a repulsive gravitational force. So this is most likely, so far, the nature of dark energy, and agree with the all current observational data. But still, there are a lot of other models which agree with the observational data. So we are currently not sure if this is the theory of dark energy or something else is the theory of dark energy. Nevertheless, whatever theory of dark energy it is very different from what we understand so far. The particles is not going to be the particles. It's some kind of force, some kind of awakened force, because it's becoming more and more important. And that force is very special. And in Chinese, we probably call this kind of special force, if you understand some Chinese characters. And so this character comes from here, which means that eventually our universe would become very lonely. And this is indeed the best guess of our universe, that our universe probably indeed will become quite lonely in the future. And here, I have to say that, again, we are not sure about it, because if we are trying to infer hundreds of billions of years after now, so we need to, on the one hand, understand the theory very well, because otherwise we are not sure what's happening in the future. We cannot predict. And now, in fact, we cannot predict confidently. And even if we want to extrapolate what we observe so far, we need very high precision experiments. And currently, a lot of experiments are going on, especially the galaxy surveys, to measure the nature of dark energy And we expect an order of magnitude improvement in the relatively near future. But this is not what we understand now. We hope in the near future we can have much better understanding. And here to close the talk, I'm going to quote Rumsfeld. He got an award this year, the Foot in Mouth Award, meaning that he's saying something not really making any sense, but it's something that makes sense in physics. You know, he's not a physicist, but nevertheless, what he's saying is there are known knowns. That are the things that we know. And we also know that there are known unknowns. That are we know there are something that we don't know. But there are also unknown unknowns that we know there are something we don't something that we even don't know. We don't know. Yeah. So to make an analog, so this is the figure of HKUS, the photo of HKUST. So if we imagine science like a cycle, then in the center of the cycle, in the center of the circle, that are the known knowns that we know. And at the boundary, we are doing research about something that we know we don't know. So by we know we don't know, that are the things that we can ask questions. And we can, using scientific method, to approach that questions. But actually, there should be a vast sea of the questions that we cannot even ask the question in science. So they correspond to the unknown unknowns, which are the things that we even don't know, And hopefully in the future, we are pulling the sea of unknown unknowns to known unknowns and eventually known knowns. That's my talk. Thank you.